inference in many-adapter environments may bring benefits, but its current execution may be inefficient.
Inefficiencies in LLM inference, for example, the heterogeneity of requests or loading overheads. I mean, how widespread are these issues?
It's a well-known algorithm that has been applied for other reasons, right? For supercomputers and other things.
Hello everyone, welcome to the very first episode of Tech with Per. Here we explore some of the new innovations in AI. Today I'm joined by a couple of innovators from the University of Illinois who recently came up with an innovation to make LLM inference more efficient. When it comes to deploying production-ready GenAI applications, efficiency is the top priority for any business leader because the total cost of ownership depends on how efficiently the application utilizes the available hardware resources. The study proposes some novel ideas to optimize the efficiency of LLM inference systems. Today, we'll learn more about their research, how it's changing the game, and what it means for the future of GenAI. So let's welcome our guest, Nikoleta, Josep. Thank you so much for joining us, and I'm so excited to learn from you.
Thank you for having us.
My pleasure. So Nikoleta, I understand that you have a short presentation for us. Maybe we can start from there and then jump into your research. How does that sound?
Right, that sounds good. Yes,
Right.
I have a short presentation to give a brief overview of what this work is about.
Awesome.
Great, so I guess we can start.
Yes, I can see your screen.
Great. Okay, so hello everyone. Today I'm going to present our recent work, Chameleon, Adaptive Caching and Scheduling for Many-Adapter LLM Inference Environments. So large language models are everywhere. Generative LLMs have seen an exponential growth in recent years. So they have been integrated to numerous technological advancements and applications in different domains. So as their popularity increases, the number of online queries in data centers has seen an exponential growth, has become substantially larger. So these queries typically want to target downstream tasks. So these different tasks also require different or special purpose fine-tuned LLMs. And to achieve their highest accuracy. So this is very resource and energy demanding. So recent solutions such as adapter-based techniques such as LoRa or low-rank adaptation have been proposed to alleviate this problem. So what LoRa does is that it induces small low-rank trainable matrices to speed up fine-tuning, basically. So it fine-tunes a small or low-rank subset of the base model's parameters for specific tasks. LoRa was initially designed to speed up training and to efficiently store the model parameters, but has become an emerging solution for online inference. So different LoRa adapters can have different sizes, as different tasks may require different levels of accuracy. So here we can see how typical LoRa online service systems look like. What these typical systems do is that they decouple each model's base from fine-tuned adapter parameters, and then they allow different collocated large language models to share a large fraction of their memory. So here we can see the organization of such serving systems. So on system initialization, the base LLM is transferred and is loaded in the GPU memory from the host. And then we can see a scheduler on the host that manages the incoming request in a first-come, first-served manner. And then it updates the batch to be executed on every iteration using iteration level scheduling, which is the state of the art. Before it sends the batch to the inference engine on the GPU, the scheduler makes sure that the system loads any missing adapters that are required by the request in the batch. And then once there are no running requests that use a given adapter, the adapter is discarded from the GPU memory, and that is to make a space for the incoming requests. So based on these insights we got from our characterization, we designed Chameleon, which is an LLM inference serving system that is optimized for many adapter environments. So Chameleon leverages underutilized GPU memory to implement a software-managed adapter cache. And then this cache stores the adapter's weights in GPU memory, removing the adapter loading off the critical path, the inference request critical path. And then to improve the request tail latency, Chameleon also uses a multi-queue non-preemptive scheduler that provides an express lane for short requests while guaranteeing that long requests won't starve. Here we can see an overview of Chameleon's architecture. So to handle workload heterogeneity, Chameleon wants to classify all incoming requests based on their total size. So every request first goes through an output length predictor. We use a small large language model, BERT model, to classify the request's output length, and then given its input length, the input prompt token size, and then its adapter size, we get the weighted request size. And then Chameleon uses this weighted request size to categorize requests into classes, for example, small, medium, or large. And then it admits them to different request queues. So at every iteration, Chameleon uses requests from all queues while checking what their assigned quotas are, because all the queues have some specific assigned quotas. So each queue is assigned some amount of GPU resources that the request from that queue can consume at each iteration. So the scheduler creates a fast lane for short requests, preventing their head-of-line blocking. But as I also mentioned earlier, it also admits requests from all queues, guaranteeing that no request will starve. So on every scheduling decision, Chameleon also invokes the cache manager. Cache manager is a software managed controller that manages the Chameleon cache. So the manager is assigned to fetch any necessary adapters that are required by the requests to be scheduled and to discard any idling adapters when the available GPU memory is not enough to store the incoming requests, input, output, and KV cache entries. So here is an overview of our evaluation methodology. So we use the following hardware platforms and the large language models for our experiments: A40 and A100 NVIDIA GPUs, along with an AMD EPYC processor with 48 cores. We used the Llama family model, 7, 13, and 30 billion, and we used open source production traces from Azure that we paired with the adapters of different sizes or different ranks, and for that, the adapters followed the parallel distribution. Our baseline is LoRa, state-of-the-art serving system for many adapter environments, and we used specific SLOs. So overall, what we understand is that LLM inference in many adapter environments may bring benefits, but its current execution may be inefficient. For that, we propose Chameleon, an efficient LLM inference serving system for many adapter environments that has two main optimizations. One is adapter caching, where Chameleon minimizes adapter loading overhead on the critical path, and then scheduling to alleviate head-of-line blocking for requests that are highly diverse in execution times and memory. So overall, Chameleon reduces P99 TTFT latency by 80.7% and then improves throughput by 1.5 times. Thank you.
Awesome.
And
thank you so much.
You can see our preprint available on archive.
Awesome. Thank you so much for the explanation, Nikoleta. I read through your research paper, and obviously I have a few questions and doubts on that. The first question is about the challenges that you mentioned in the paper, like the inefficiencies in LLM inference. Right. For example, the heterogeneity of request or loading overheads. I mean, how widespread are these issues? Is it applicable to every LLM deployment? Or is it applicable to only the model deployment that use adapters? Right.
So yes, our work, Chameleon, specifically targets many LLMs in many adapter environments. So our optimization techniques, that is adaptive caching and scheduling, target LLMs that share a big portion of weights, but also have their different adapters.
Okay.
Nevertheless, those techniques can be adapted and used in more generic LLM environments. For example, scheduling also applies to even conventional LLM inference serving, where we have only one base LLM model, but even then we may have diversity in requests. So scheduling definitely applies in the general scenario of LLM inference serving. When it comes to caching, yes, we indeed focus on having an adapter cache, but this concept may be also used in scenarios such as mixture of experts, where we have LLMs that use many experts. So for example, one iteration, only a portion of the LLM's parameters are used, and not the entire LLM. So these workloads are emerging. So
these are more
yes,
like
I would say this is a more general optimization technique.
Yeah, these are more like the state-of-the-art way of deploying GenAI applications, right? Using the mixture of experts, because in a typical enterprise production-ready scenario, there may be multiple modalities involved, or multiple tasks may have to be inferred from a group of LLMs. So it's always best to use few different models, maybe SLMs or LLMs, which have different accuracies on different types of tasks. And what is something that is overlooked is people forget to focus on how to efficiently do this inferencing. So that is one area that your research is addressing, right? Exactly, yes. We want to efficiently serve requests when it comes to resources, and the execution to be fast, and at the same time to be highly accurate. And LoRa adapters and in general adapters are the way to go. It is an emerging workload for sure. In terms of performance gains, right? There is two ways to do that. One is the traditional way, letting the inference overheads be there, and not dealing with the heterogeneity of requests. But of course, your method, your approach is, as I understand, is making use of the idle GPU to cache the frequently used adapters or the popular adapters. So that's what your methods are. But what is the difference that you have observed in the performance? What is the difference? What do you mean? Which difference? It can be in terms of TTFT or the latency that you have reduced. Yes. So we observe a P99 TTFT latency reduction by 80.7%. So that is for high loads. Yeah. What we observe in high loads is actually that most of the times GPU memory is actually not that underutilized. Mm-hmm. The general case is that it can be underutilized in many
time intervals throughout the workload execution, but that can not necessarily be the case. What we observe from our experiments is that we do gain actually many benefits, even from the scheduling part in high loads, and that can be, this 80.7% reduction can be in orders of many seconds.
Okay.
These numbers we also have in the preprint.
Okay, yeah. So also one of the diagrams that you have shown in the preprint, which shows the usage of the GPU over time, right? I noticed that the GPU is mostly used. I mean, it's used to close to 100% only for a short duration of time, and for the rest of the time, it's mostly like maybe 30 or 40%. But as I understand, when it's close to 100% is the time when the demand is higher, when more inferencing is happening. So my doubt is that if at that point of time there is less idle GPU available, but your method works around loading these popular adapters using the idle GPU. So my doubt is, how does that work during that time? Because during the high demand time, the adapters need to be more needed, but there is not enough space to load the adapter. So how does it work at that time?
So this diagram, of course, takes into account the necessary adapters that need to be loaded in the GPU. So no matter what happens, when requests are being executed, then the adapters that are for these requests have to be in the GPU.
Okay.
So even if we don't have any idle adapters, these adapters are taken into account and are already in the GPU loaded. So what this diagram actually shows is the GPU memory usage. We do take into account the necessary adapters there, and if in a scenario where the usage is always 100%, that means that there is no room or space for adapters that are not currently used. So adapters to be cached. So yes, in such a scenario that is not very frequent, that doesn't happen very frequently, yes, we wouldn't benefit from our adapter cache, but we would still benefit from our scheduling optimizations.
Okay, the scheduling optimization is more like to reduce the, increase the output, right? I observed that you discarded the first in first out scheduling, and also the simplest task first. That is not also discarded in your research, but you are focusing on, if I understand correctly, the WRS weighted resource rank. I forgot the expansion. So that's what you're using, right? So can you please explain a bit on that?
Right. So we tried different state-of-the-art scheduling techniques, such as first come, first served, and then shortest job first. So the disadvantage or the downside of first come, first served is that it admits requests in the order of admission to the system. So it might introduce head-of-line blocking. What this is that it may admit few long requests, and then many short requests, for example, will wait for this long request to execute, and their overall time to first token will increase substantially. So then the overall P99 tail latency and also median latency increases.
Okay. So
So that's the bad thing with conventional first come first served schedulers. Other works try to explore shortest job first scheduling techniques in a scenario that we know the request size in advance. That also is not good enough, since shortest job first prioritizes the small jobs over the long ones, and then what happens eventually is that the long jobs starve, and we don't want that.
Yes.
We want to maintain fairness, and at the same time, every request, small or large, to be executed as fast as possible. And that's why we came up with this multi-queue non-preemptive scheduler.
Okay. And what is the difference in your approach for this scheduling?
The difference is that we have multiple queues that admit requests by their size, short, medium, or large. And in every iteration, the core difference is that we admit requests from every queue. So in iteration number 1, we would admit small, medium, and large requests, even if all the large requests would arrive before the small ones. And in that way, we do create a fast lane for short requests to be executed. But at the same time, since we do continue admitting large requests, we can guarantee that large requests won't starve. It's basically like we do perform some load balancing with using these multiple queues.
Understood. That's very interesting, but that's another thing that strikes me. When it comes to load balancing, when you're constantly loading and unloading adapters, it has to affect the end TTFT or the latency, right? But your end result is actually reducing that. But I'm confused there. It's supposed to be increasing, right?
Yes, loading and unloading adapters on the critical path is, of course, a different source of overhead. So in this work, we break down the overheads in loading the adapters and actually in how we schedule the requests. Mm-hmm. So that's why we do have caching and scheduling. And those two optimizations actually work synergistically and try to minimize both sources of overheads. I mean, if we are talking about the scenario that we have so much load, I don't think, and where the server's capacity is not enough to handle it, yes, of course, any system would break down because it wouldn't be operational. Mm-hmm. We're talking about potential and alleviating these extra overheads that can be alleviated.
Okay.
I mean, in a scenario where memory usage is 100%, yes, we wouldn't benefit from the caching optimizations, but we would still benefit from scheduling. Okay. But it's not that someone else would do better.
Understood. And regarding the eviction policy that you have described in the paper, the weighting coefficients F, R, and S, how did you come up with those? How sensitive are these weights to different workloads or the heterogeneity of the requests?
So we did perform thorough sensitivity studies with open source traces and also different synthetic workloads. What we found out is that for different coefficients, actually the difference in performance can be like at most 10%. So for that work, yes, we did use the coefficients that worked best for our system, and this is something that actually we want to improve, and this is like ongoing work to come up with a way, probably using maybe machine learning, that will adapt those coefficients over time.
Understood. And for your scheduling, the multi-level queue scheduler, was there any trade-off? Obviously, it helped to make the inference more efficient, but was there any trade-off? Do you have to sacrifice on some other aspect of the inferencing?
Right. I mean, there is the trade-off of having multiple queues to coordinate and to manage. Mm-hmm. This is an overhead. Our system uses prediction techniques to predict the overall adapter size. Even if we don't predict very accurately the output size, mm-hmm. Our system is still robust to mispredictions and can handle different request sizes. Like, for example, if a small request goes to the wrong queue, we are robust to that, and we have experiments on that in our evaluation section. So I would say that the main trade-off is to handle multiple queues and probably to the dynamic part of like when we dynamically change the number of queues and the number of quotas. This is something that shouldn't be done statically, and we take care of that. But this is like a trade-off, like the way to manage this. Nevertheless, these overheads do not affect the overall execution time. We find out.
Okay. And is there any particular scenario where Chameleon's performance could degrade compared to the baselines, or if there is, how do you plan to address those?
Did you ask, if I understood correctly, if there is a specific scenario where our system underperforms?
Yes.
So I would just say no. We just tried, we did many experiments with many workloads, synthetic and these open source traces. We didn't find a scenario where Chameleon underperforms the baseline, because caching just minimizes the overheads of loading and unloading adapters, and actually our scheduling techniques are smarter than the conventional first come first serve way. So I guess both systems break down at some point, but what we find out is that we may break down at higher loads.
Okay.
Not earlier.
Okay. And did you also experiment with other modalities, maybe diffusion models, or or audio models, or did you just experiment with text models?
Yes, for that we did experiment only with text models, and with different adapters of different size for different base models. So yes, this work is, I wouldn't say limited, but focused on language models that have text, not audio or video. And yes, we use different base models of different size, and then on top of that, we use different number of adapters of different size for these base models.
But ideally, it should work, right? Even if you haven't done any experiments or benchmarks specifically for diffusion models.
Yes,
but architecture-wise, there is no much change happening. Is that correct?
Yes, that should be the case. We are actually we're thinking whether we should go and explore multimodalities, but this is still under discussion. Okay. Multimodal has its own challenges. How actually someone will, how the inference itself is performed, what kernels are used, and what other overheads may occur there. But this is orthogonal to our work.
Understood. So the reason why I asked is because I frequently talk to these clients from all around the world. These companies want to deploy multiple modalities in their production setting, right? So they have to constantly inference from vision models or text-based models, and these would be more heterogeneous in nature. The loads will also be very dispersed over time, right? There may be more requests at some time, and there may be very less requests at some point, at some time, right? So managing the inference request, making the best out of the hardware infrastructure is key to these clients, because the total cost of ownership depends on how well their hardware infrastructure is utilized, right? So yes. One question I have on that point is, have you done any estimation about how much energy this particular method is saving?
Right. So we don't have any numbers published in this work, so it's not that we focused on energy reduction, but it should be proportional to performance gains, and should probably be sublinear to performance gains that we have. Yes, because we can reduce energy by minimizing moving of data movement, and also with the smart scheduling. Yes.
Understood. In your paper, you pointed out that this method could reduce the latency, the P50 TTFT by up to 80.7%, and
Right.
the other one, sorry, the P99 by 80 and P50 TTFT by 48%. So I think this can be correlated in a way to the proportional energy reduction, right? The reduction in latency by X% could translate to a percentage of reduction in the total energy, right? So yeah.
Right.
Yeah.
I think that would be the case. I mean, of course, P99 latency, we have more reduction there because because our scheduling technique actually wants to basically works more for the tail latency, but at the same time alleviating head of line blocking and then having no starvation also helps the median latency. Yes.
Awesome.
But I guess, yes, the energy numbers should be proportional.
Awesome. And have anyone tried this in a production environment? Did you get any feedback from any organizations or any businesses who tried this out?
Yeah, so we are in discussions with IBM to actually open source the code. So the code is currently built on top of SLoRa, which is state-of-the-art serving systems for Many-Adapter environments. But we would what we got is that we should integrate our work to VLLM, which is a more general and highly supported LLM inference serving system.
Awesome. Also, the industry trend is going towards, due to the cost component, companies are more leaning towards running SLMs on CPUs rather than large language models on GPUs, because the GPU component itself is very costly. Acquiring them, the wait times, it's all a headache for business owners, and as a result, they are mostly leaning towards SLMs on CPUs. So my question is, can this method be adapted to CPU only infrastructure where there is no GPU involved?
Right. Yes. So one other possible direction that this work could take is actually for the scheduler to identify when it's better to send requests to be executed on CPU, and under what scenarios it would be best for the batch of requests to be executed on GPUs. That's one potential scenario. And for the caching as well, it would work synergistically with the scheduler. So yes, it would decide whether to load an adapter on GPU, or is it better, since an adapter is already on host or on CPU, for the execution to take place there.
Awesome. And how do you see Chameleon's, this adaptive caching method evolving in the future? Do you see any scope of improvements?
Yes. So as I said, Many-Adapter, inference in Many-Adapter environments with adapter-based techniques is an emerging workload. So I could see Chameleon evolving and getting these techniques to be applied in different workloads, such as mixture of experts LLMs, where they have also their challenges in a similar manner, but then even more demanding. Yeah. So I could see Chameleon getting applied there, and also I could also see Chameleon getting applied in a much larger scale.
Okay.
To be part of a bigger system that would schedule requests in different nodes, for example.
Okay. Also, one question that I had in my mind earlier, but I forgot to ask. You mentioned that you are predicting the token, the output token length using a separate model, right? I think you mentioned BERT for that. So
yes.
Using an additional model in the process, wouldn't that affect the the workload?
Yeah. So this actually no. This overhead is not substantial, at least for the inference part. So what what is done is that this model takes place in the CPU. The model is small enough for this to be done there. And then we actually took this technique from earlier literature work. Okay. So we verified that this works with high accuracy as well.
So there is no substantial overhead on that aspect?
No. And that's what previous work claims, and that's what we verify as well.
Okay. Awesome. I guess I asked all the questions I had on this research. Is there any additional points that you have to emphasize?
Harsh, I was just simply saying that we encourage the listeners to look at the paper, to look at the multi-queue scheduler. Mm-hmm. It's a very simple multi-pass scheduler. Yeah. You have multiple queues. You do multiple passes. In the first pass, you go through all the queues, and you have a quota for each of the queues, and you take according to the quota. Mm-hmm. If you still have extra capacity, you do another pass, right? And then you also grab additional things that fit. Simple that. Right? So this way, you ensure that you pick from all the queues, right, according to the quota. And if there's extra capacity, you grab whatever is left. Okay. Without starving the short jobs and without, having the long job, without starving the long job and without line blocking for the short ones.
That's understood. So in a nutshell, what your method does is, if there are additional or available resources, the scheduler and the multi-queue scheduling makes the ender process more efficient. But if there is a GPU crunch, if it is 100% used up, the system would still work in its original efficiency. But if there is idle GPU available, you have an opportunity to boost up the efficiency by maybe bringing down the latency by 80%, or if it's another benchmark, it's 50%. So there's a substantial increase that can be achieved in the LLM inferencing if there is idle GPU. So that's the whole offering, right?
That's right. It's a well-known algorithm that has been applied for other reasons, right? For supercomputers and other things. It improves the efficiency.
Awesome. Well, that's all question I have for now. I learned a lot. Thank you. And I wish you all the very best for your future endeavors. And once again, thank you so much for taking time to join the session.
Thank you.
Thank you so much for having us.